Um, I think it's time still. You guys can start.
Hey, hello everyone. I hope you're having a wonderful afternoon so far. I just want to formally welcome you to Group 3's final aerospace design presentation. Today we will be sharing more about our aircraft, which we named the Silver Surfer, and just taking you along the journey of our initial estimates, analyses, design process, everything that led to our final result. We're going to start with a quick team introduction.
Hello, my name is Gabriel Lemos.
Hello, my name is Giancarlo Greco.
Hi, my name is Joshua Kuri.
Hello, my name is Chandler LeBlanc.
Hi, my name is Janae McLeod.
Hi, my name is Dwani Patel.
Hi, I'm Devin Pryor.
Hello, I'm Juan Rodriguez.
Hi, I'm Sabrina Vihek.
And I'm Thomas Vetter.
So with that, I'm going to get into our mission requirements. So what we needed to include and what our aircraft had to be capable of. So there had to be a ground rolling takeoff within 40 feet of the starting line. And after takeoff, 3 laps had to be completed, the laid out course, which is shown below, and it had to be completed in 5 minutes. The aircraft must also not sustain serious damage at any point during takeoff, flight, or landing. And the maximum dimension of the aircraft, whether that be lengthwise or spanwise, had to be less than 8 feet, and the gross takeoff weight had to be less than 55 pounds. It must be propeller driven, electric powered. The battery packs can't be altered, and they have to be commercially produced. So now that we knew mission requirements, we're able to narrow down our search to look at aircraft on the market that are capable of the requirements that I just listed. So after that, we researched 4 model aircraft that were propeller driven, PLA printed, radio controlled, lightweight, and affordable. So the average wingspan of all of these was about 3 to 4 feet, and the takeoff weight for all of them were around 2 pounds. So to get into more of the specific estimations, we referred to the Eclipson Model A, which is pictured on the right. And the wing loading we use is the same as the Eclipson Model A, just converted into metric units. And for the power to weight ratio, the Model A's motor had a power that was capable of 100 to 300 watts. So just that divided by the weight resulted in a power to weight ratio of 137 to 411 watts per kilogram. And for the lower half of this range, that's what was necessary for our aircraft because it was more low speed aircraft that could perform basic aerobatics, didn't have to be more complex than that. And then there wasn't much research on the coefficient of lift for RC airplanes, but we used a value of 0.8. And then for the coefficient of drag, used a value of 0.06. So our lift to drag ratio was 13.33 for the entire RC aircraft at straight and level flight. But just to note, this value should be greater for just the wings. That should be around 20 to 80.
So when we chose the motor and battery that we were using for our plane, our design, we realized that the weight would be more like 1.81 kilograms, which is around 4 pounds. This new weight gives us a new wing loading of 9.09 kilograms per meter squared. And the aspect ratio was determined from a book, and it said that for most home-built aircraft, the aspect ratio is 6. Using these parameters, we got a wingspan of 0.199 meters squared. A wing area of 0.199 meters squared with a wingspan of 1.09 meters and the standard mean chord of 0.182. We chose a taper ratio of 0.4, and this left us with a chord root of 0.260 meters and a chord at the tip of 0.104 meters. When determining what airfoil we should use, we researched popular RC airfoils online, and we found that the 2 most popular airfoils for RC airplanes are the Clark Y airfoil and the NACA 2412 airfoil. However, after further research, we found that the NACA 2412 airfoil did have better flight characteristics and was actually just becoming more popular than the Clark Wyatt airfoil for RC use. So we chose that one. We had a high wing design for stability and accessibility purposes. And the design was made with 0 degrees of sweep in the leading edge. And the main reason for this was because we had a carbon fiber rod that connected both wings together, and we felt it would fit better if there was no sweep at the leading edge. And we also had a dihedral of 0 degrees. The wings were also designed with ribs that had holes cut up in them so that the carburetor could fit through them.
As Josh mentioned, we had our set criteria for the size and dimensions of the wing. So from these parameters, we used the program XFLR5 to analyze 3 main wing designs. One with 0 degrees of sweep and no taper ratio in pink, one with 5 degrees of sweep and a taper ratio of 0.61 in blue, and one with 0 degrees of sweep and a taper ratio of 0.4, and that's in green. These wings were analyzed at a constant speed, and the top picture shows the local lift distribution across the wing, with the green design following the ideal elliptical curve best compared to the other designs. And then the next graph shows the coefficient of lift over the coefficient of drag at the angle of attack required for cruise level flight. And given that all other parameters are equal, the higher CL/CD ratio corresponds to more lift produced by the wing and a more effective design. Therefore, all the data pointed to choosing the green design, which had the most taper. And then at the stall speed, the coefficient of lift, the coefficient of drag, and the Reynolds numbers were computed, and they are listed there on the slide.
For the control surfaces of the wings, we found that ailerons have a span that is about 60% of the span of each wing, and they have a chord that is about 20% of the chord of the standard mean chord of the wings. Also, since this was a small model plane and not very heavy, we decided that we did not need flaps for taking off or for landing.
Regarding the fuselage design for our radio controlled plane, we based the shape of our fuselage design on the Cessna 152 as reference, with some alterations to meet our design needs. One of the key advantages of the Cessna 152 fuselage design is its simplicity and ease of manufacture, making it popular choice among RC planes. The straight and streamlined shape of the fuselage provides a strong structural frame, which allows for good stability and control during flight. This rigid geometry can provide excellent support for our RC plane. It is important to note, however, that this type of fuselage is not suggested for major stress loading aircraft. However, since our purpose was to achieve a lightweight RC plane, this was not considered as a concern. For the sizing of our fuselage, we researched that the length can be calculated as approximately 75% of the aircraft wingspan. Therefore, we determined its length to be 0.8183 meters based on our wingspan. To achieve the precise sizing of the fuselage and correspond with the shape of the Cessna 152, we divided the fuselage into 3 main sections. The first section accounted for 20% of the fuselage length from the nose of the fuselage to the wing's leading edge. The second section accounted for 40% from the wing's trailing edge to the horizontal stabilizer's leading edge, and the remaining length was accounted for the tails. For the material used in our fuselage, we started with lightweight PLA to decrease the weight of the plane, while ensuring lift was achieved in takeoff and straight level flight.
Due to our relatively small size and slow speed, we decided that one motor and one propeller was enough to provide thrust for our plane. When we started the motor selection process, as Josh said earlier, we realized the weight estimations were too low at first, especially because, and also the power to weight ratio was too high. And that was especially because the power systems itself were already 2 pounds. So our plane was definitely going to be much heavier than that. So our new estimations for weight was around 4 pounds, which is shown there, 1.81 kilograms, and power to weight ratio of 120 watts per kilogram. Then we estimated the efficiency of propeller and motor as 80% each, resulting in a total efficiency of 64%. And then we used the equation shown to find our power consumption of 339.4. With that power consumption, then we selected a range of kV ratings that for our motor, which we found to be between 800 and 1500. And we went for the lower values in that range because we want a slow plane again. And then the propeller diameter was initially estimated between 20 to 25% of the wing size. And then we used motor spreadsheets to combine motor, propeller, and battery to find the necessary power input we needed.
So once we determined the estimations for each of our components, we set about finding the most ideal component for our propulsion system. We initially landed on the Tempest 2814-1050 motor. However, because it wasn't available, we went for the Tempest 2820-840 instead. This had a power consumption that was lower than our initial motor, and it was actually much closer to our predicted power consumption. Having a higher consumption meant having a greater thrust, and this could prove to be difficult when controlling the aircraft when it's in flight. Moreover, the power system weight matched exactly to our initial estimation, which dispelled the need for a second iteration. The battery we selected was the 3300 mAh battery. This was also based on availability, but it was compatible with both the motor and the propeller, more so because it had 4 cells, which was required to reach our power consumption. And lastly, we selected the 10x5 propeller. This wasn't our first choice. We initially opted for the 8x6. However, in terms of assembly, we realized it wasn't practical because the propeller wasn't large enough to be compatible with the shaft of the motor. And this 10x5 propeller helped not only in terms of assembly, but also in terms of its 10-inch diameter being around 25% of the aircraft's 43-inch wingspan.
So in regards to the landing gear, we decided on a tricycle configuration due to ease of handling, maneuverability, and more control in comparison to the tail dragger. Based off the center of gravity, the front nose gear was adjusted to be about 40 degrees in reference to the ground, and whereas the rear wheels was approximated to be about 6 to 20 degrees, which we resulted in about a 12 to 15 degree range, depending on how heavy the tail would be. The length of the front nose gear was dependent on the propeller dimensions, just to make sure that we wouldn't propeller strike and hit our front end. And we also resorted in a shock absorbent front nose gear, which caused to help and assist in landing. The rear wheels came from a Cessna 182, which was in comparison to our fuselage, and it was made out of spring steel for durability and was malleable.
We also conducted a structural analysis on the wings of the aircraft to make sure that they would maintain their integrity during typical flight conditions. To do this, we researched the yield strength of PLA, and we picked a factor of safety of 3 for our craft. Based on this, we calculated the maximum allowable stress in the design to be 16 megapascals. Based on some more research, we also found that the maximum loading factor for RC aircrafts is typically around 5. Using the weight of our craft and the maximum loading factor, multiplying those two together, we were able to find the maximum lift force expected to be experienced by our wings was 44.5 newtons. Now, comparing that lift force to the integral of the elliptical lift distribution shown below, we assumed an elliptical lift distribution because we designed to approximate an elliptical lift distribution, and also an elliptical lift distribution is the ideal distribution that results in the least drag in an aircraft. So we were able to equate those two to each other now that we knew the lift, and then by solving for the constant of the elliptic lift distribution, we were able to complete that equation. And then we did the double integral over the wingspan of that to calculate the moment, and the moment is known to be its maximum at the root of the wingspan, which we found to be 5.15 Newton meters.
As Devin mentioned, we now defined our maximum allowable stress and our bending moment at the root of the wing. So to ensure that our stress is less than the allowable, we had to compute the distance from the neutral axis C and the second moment of area I to complete the classic MC over I equation for stress. So to compute these values, we first approximated the cross-section of the airfoil as an I-beam, and that the height of the I-beam is the same as the maximum thickness of our airfoil, and that the maximum distance for the neutral axis C is half of this value at 0.01356 meters. So now that we have distance from the neutral axis, we can solve for the maximum allowable second moment of area for our design, known as the equation I equals MC over sigma max. From this, we can then solve for the thicknesses TF and TW shown as on the diagram, which correspond to the wing wall and wing spar thicknesses of our wing design. And these values are 0.0012 meters for the web and 0.008 meters for the fins of the I-beam. And these thicknesses were computed to minimize the weight of the wing while meeting the second moment of area requirements I. And they also match with the PLA layer thicknesses.
For our tail design, we went with the conventional configuration because of its light structural weight, high stability, while still providing enough control for our purposes. The tail selection process was based mostly on a historic approach. Most of the values here are based on Reimer aircraft design, and also some other sources that agree with Reimer. We selected a NACA 0012 as our symmetric airfoil for the tails. The location, the starting point was 60% of the fuselage length for both, which is a common practice. And then the vertical tail was moved forward to avoid blanketing of the vertical tail, which happens at high angles of attack when the horizontal tail blocks the airflow to the rudder, making it inefficient. Then we use the equations shown in the table for area for SVT and SHT, which come from the definition of volume coefficient, which is a way to non-dimensionalized way to relate area of the tail and area of the wing, and those come from moment equations. Then we also got the aspect ratio and a taper ratio from historical data. And we used the aspect ratio and area to find the span and the standard mean chord after that. The sweep angle, we knew that for horizontal tails, they're usually 5 to 10 degrees more than the wing. And the vertical, they were usually between 35 and 55 degrees, and we went for the lower end because for slow speed aircrafts, that's not needed besides for aesthetics.
This tail design configuration of the RC plane had to consider also control surfaces for both horizontal and vertical tails. Research suggested that the elevator's length should be estimated to be the same as the horizontal tail length and have within 20% to 40% of the total area of the horizontal stabilizer. It is important to note that small elevators, which are around 20% of the total horizontal tails area, demand large deflection angles, which at the same time reduce efficiency. Meanwhile, large elevators, which are at around 40% of the total horizontal tails area, can be difficult to control for small deflection angles that can considerably change lift. As our RC plane does not require drastic changes in pitch, we selected an elevator of 30% of the total horizontal stabilizer area for our design. Regarding the rudder, research suggested that its length should be the same as the vertical tail's length and 50% of the total vertical tail's area. However, we opted for a greater rudder so that the RC plane can perform quick turns over the layout course. Overall, our tail control design aimed to achieve a balance between efficiency and maneuverability.
We also conducted a stability and control analysis on the aircraft to characterize its flight characteristics. The stability and control analysis can be broken down into a static stability analysis and a dynamic stability analysis. For the static stability analysis, we considered the CL, CM, and CN, which represent the moments about the X, Y, and Z axes respectively. The plane is statically stable when these moments cause the plane to return to steady and level flight after a disturbance is experienced. So the graph in the bottom right of this slide, where all of those lines meet, is the trim point. The stable line is the green line. When the angle of attack is greater than the trim point, it's a negative CM value that will cause the plane to return to steady and level flight. If you take the derivative of CM with respect to angle of attack, it would be a constant negative value, indicates stability. And it's similar to the other two ends.
As Devin mentioned, there are three derivatives that characterize the static stability of our aircraft. These are the derivative of the roll moment, CL beta, the derivative of the pitching moment, CM alpha, and the derivative of the yaw moment, CN beta. Their theoretical equations are at the top of the slide, and these values are the criterion that determine whether the plane is statically stable. So to compute these values, we used the program XFLR5 and did a stability analysis of our plane. And for CL beta, we had a value of negative 0.0431. And for CM alpha, we had a value of negative 0.705. And for CN beta, we had a value of 0.141. And since CL beta and CM alpha are negative, they are seen as statically stable, while CN beta is positive, which means that it is also statically stable.
So moving on to dynamic stability. Dynamic stability is the amount of time it takes for an aircraft to return to equilibrium after it's been displaced, and it's characterized by the following modes. So the short period mode is characterized by heavy damping of oscillations. This mode only lasts for a few seconds. The Fugoi mode is the motion of the aircraft pitching up and down. The roll mode is as the aircraft rolls, so when the wing goes down, the angle of attack increases, and as the wing goes up, the angle of attack decreases. The Dutch roll mode is a combination of the roll and yaw acting adversely against each other. So as the aircraft rolls in one direction, it yaws in the other. And lastly, the spiral mode is the result of disturbances in the side slip and the yaw. Now, this mode, it takes a long time to destabilize, so its stability and or instability can be ignored. So we computed our eigenvalues using the XFLR5 software, and it returned the following eigenvalues. A negative real value indicates stability, and a positive real value indicates instability. So for the short period mode, we got two extremely large negative real values, and due to the heavy damping of oscillations, our imaginary value was very, very small, so we approximated it to be 0. So for the short period mode, we had stability. In the Fugoid, roll, and dodge roll modes, we also had negative real values, which means that the aircraft was stable in all of these modes as well. Lastly, for the spiral mode, we did end up with a positive real value. However, despite this indicating instability, like I said before, it takes a very long time to destabilize in this mode, so the stability can be ignored. After analyzing all of these modes, we can say that our aircraft was dynamically stable.
So in regards to our first test flight, we did have a successful takeoff, but we did have a short flight time. We realized early on that that's where we wanted to switch our mid-wing design to a high-wing design because we couldn't get our wings to be as stable as we wanted them to be. And that's also where the spar came in. When we were having trouble with our 3D print, so we also had thicker and larger fuselage improvements to be made, and then we added better landing gear alignment.
For our second test flight, we implemented all the needed changes from the previous flight, and this resulted in a much smoother takeoff and a much longer flight. And the plane also had an increased controllability. However, we did crash land due to the strong winds. Therefore, we had to have extra improvements to be made for our third test flight.
For our final test flight, we printed the fuselage out of PLA instead of lightweight PLA to make it stronger. We also lengthened the nose by 2 centimeters to move forward the center of gravity even more. And then we added ribs in the wings for greater structural support. All these corrections resulted in a much longer and stable flight. And luckily we had weaker winds during the flight, so our airspeed wasn't dramatically doubling. But unfortunately, we had an unsuccessful landing due to stall. If we were to make another model of our aircraft, improvements to be made would be better printing techniques to improve the quality of our pieces, more stable landing gear assembly to make sure they wouldn't fall off during takeoff or flight, greater control surface effectiveness, and again, still making the tail less heavy by either lengthening the nose more or reducing the amount of the fuselage between the trailing edge of the wing and the tails.
So for our old design, the original wing had a mid-wing placement, but we quickly noticed that this design combined with the narrow fuselage that we originally had didn't leave us with much access to the electronics. And so the wings also didn't have like a sturdy connection to the fuselage, and they had too much movement. So when we switched to a high wing design, we realized it gave us more access to the electronics as it was removable, and it also provided us with better stability.
So after the manufacturing and testing of the design, several changes were made to the fuselage in order to counteract difficulties faced and to create a more effective design. For instance, after the first test flight, the initial design consisted of a mid-wing that was later changed to a high wing, done with the intention of having a smoother manufacturing process when incorporating electronics to the plane, since having a hole through the sides of the fuselage basically would cause the structure to be weaker and harder to manipulate things inside once everything was placed. And of course, calculations were revised to make sure that this change would not affect their previous calculations. Also, the thickness of the fuselage was doubled in order to increase the strength of the structure. At first, it was 0.4 millimeters thick, and it was changed to 0.8 millimeters. After the second test flight, some slight changes were also made. For example, instead of having a straight hole on top of the fuselage, we made a hole that was tilted following the curvature of the fuselage, so that the wings were able to be mounted better into the plane. Also, the front of the fuselage was extended approximately 2 centimeters in order to have more space for placing the electronics and also to bring the center of gravity forward to be able to create more lift during the test flights and prevent the plane from being tail heavy. Also, the fuselage was now printed using regular PLA instead of lightweight PLA to provide an even stronger fuselage. And this was also done taking into consideration that our motor had enough power to accomplish enough lift, even if we added more weight to it. And lastly, the holes of the servo motors were incorporated directly into the print to accelerate the manufacturing process. So as engineers, it is imperative to recognize that there's always room for improvement when making a design project. Despite making a successful project that fulfilled the requirements, there are still clearly things that the team could have done better to create an even better design. For example, more research on 3D printing could have been done in order to make the manufacturing process smoother without so many failed attempts when printing parts. Maybe better equipment for the 3D printing process, better planning from the team in order to achieve more test flights so we were able to identify more issues with the design and fix them to have the perfect plane. More practice on RC's plane maneuverability to counteract the effects that the weather had on our test flights. Also, better research to look for the best day to fly, since strong winds were a constant issue our design had to go through when flying. But all in all, I think this was an extremely challenging yet rewarding experience for our team and our development as future engineers. And we believe that this project gives us a useful first-hand experience on how design teams succeed, even when facing adversity in the industry.
Okay, here are our resources that we referenced throughout the presentation. Just want to thank you for attending and open up the floor for questions.
Thank you for the presentation. So, Jacob.
Yeah, great presentation, guys. Let's go to your airfoil selection. I think it's one of the first things you guys talked about. Yes. Okay. So I heard someone say, I don't know who covered this slide, I can't remember, but you picked one of the airfoil that you chose based off of it having better flight characteristics, but you didn't necessarily say what those flight characteristics were. What were the flight characteristics that made you settle on this airfoil over other airfoils?
So this airfoil and the Clark White airfoil had very similar flight characteristics. I believe that this one did have a slightly higher lift to drag ratio, and it also stalled at a little bit higher angle of attack, and that's why we chose this one.
Okay. That'd be nice to have that like demonstrated somewhere, and also have like a trade between your actual airfoils instead of like saying we picked this one for this reason. Another thing, why did you have popularity of airfoils as a design criteria? Like, why not just look into airfoils in general? Why was that a deciding factor?
Mostly because a lot of us did not really have experience with RC planes. And so when we were looking up what design we should use, the first thing that we looked up was like designs that most RC planes do use. So when we saw that, we saw the Clark White airfoil and the NACA 2412 airfoil, and we did like the flight characteristics that they had. That's why we chose those.
Okay, yeah, that's fair. I would just say like don't put yourself in a box when actually selecting your airfoils in terms of what RC does. If you understand flight characteristics of various airfoils, you shouldn't need to reference what's popular and what's not to choose your actual airfoil. But in general, like I would like to see some trades, like some sort of like table or like a graph that compares like all of these things. I know you guys use XLFR5 a lot. XLFR5 has a great tool to compare different airfoils, so that could have been a great tool to use here.
All right.
To the fuselage section. Yeah, right here. So why did you guys reference a Cessna?
So when we were looking online about RC planes fuselage, we realized that most of the research that we found was from gliders, and these gliders had like this let's say squared shape of the Cessna. And since we were doing a lightweight RC aircraft, we decided on this design.
Okay, so is that the same research that you used to pick your airfoils? Because an airfoil for a glider may not necessarily be the exact good choice for an airfoil for an RC plane. They're very different aircraft.
I think that was from different sources, the airfoil and the fuselage. I don't think they were the same. I think mostly we based our fuselage on RC planes that were slower and the gliders that Juan said. So yeah.
I also think that we researched different types of shapes of the fuselage, and as noted in the presentation, we also noted that it has great advantages, and basically the only disadvantage that we found with this fuselage was that it's not really effective with major stress loads, and we knew that this wouldn't necessarily affect our group.
And I
So
guess that showed that showed itself to us when in the first test flight, our fuselage didn't withstand the wings, the load on the wings, which is one of the reasons why it failed. You can see the wing went from like an anhedral to a dihedral as soon as it took off, and it was because of that. So I guess the disadvantage was really a disadvantage to us, but we overcame that with the high wing design.
yeah, and that's why we also made changes to the fuselage after a couple of test flights.
Okay. Yeah. So the actual, like, at least I saw from the first plane, the fuselage didn't really resemble the Cessna very closely at all, other than just being like an approximate cylinder. So it was just a weird point to be called out on. That's why I'm harping on it so much. You also said you calculate the fuselage length as 75% of the aircraft wingspan. Do you have a formula for that, Aware? Like, how did you calculate that?
Well, we actually cited the sources that we use for that, where we found that it is typically calculated to be 75% of the wingspan.
Oh, okay. So it's from research. It's not
Yeah,
calculated.
it's from research.
Okay, gotcha. All right. Let's talk about the powertrain. I think it's like the next slide or so. All right, so I'm a bit confused about what happened on these slides here. So it sounds like you guys had a power to weight ratio based off of what's typical for RC planes, and then you had a selected motor. And did you increase your weight estimation to try and achieve that power to weight system?
We increased our weight estimation because when we started looking at the most common power systems, like the tables, the charts of combinations of motors and propellers, we saw that all of them were around 2 pounds or at least above 1.5. And that was our initial estimation of weight in total, like in general. So we knew that the plane was going to be much heavier than 2 pounds, which is why we increased to twice as that, to 4 pounds.
So does that mean that your motor was underpowered, or I'm confused here?
So I mean, no, the thing is if we had the initial weight estimation we would get a much lower power, and like I guess it wouldn't be enough thrust because that was not the true power that we would need. What really happened was we estimated the weight wrong in the first trials. I guess we based it too much on other RC planes, and we didn't realize that our RC planes would have a power system that's much heavier. So increasing that weight increased the power consumption of this power system in general. So if we hadn't done that, our power consumption would be much lower, and we might have chosen a motor that wouldn't be able to provide enough thrust.
All right, can we go one more slide forward? It seems like there's a couple of things that happen here. So for one, you wanted a certain motor and you couldn't get it because of availability. And then you also wanted a certain prop size, but it wasn't compatible because it didn't fit the motor shaft. And your weight estimations also didn't match. So how close were you in your final design to your actual target? And
So, oh, sorry.
Go ahead.
So these our weight estimations are actually pretty accurate, especially for the power system weight, not the first weight, the estimation, the second one. When we said 1.81 kilograms, these weights shown in this table here are the power system weight. And like I said, they're around 2 pounds. So I don't know if you remember, but in the first slide where we have initial estimations, the power system, actually the plane total weight was estimated to be 0.907. So that's already lower than the power system weight.
Okay.
Which is why we changed that. And the motor availability was we saw that in lab, we already had a 2840 available. So we try to change our design to match that. So we could start like, we would already have the motor, not have to order it. Which is why we made that change. But it ended up being better because our power consumption before was way too high. It was like 100 watts over what we needed. And then it went down to like something closer to the value we needed.
Okay, yeah, a lot of these questions I'm really just asking for clarification. I think the way this information was presented was a bit confusing. So you can work on the storytelling a bit there. One thing I did hear though is that we did change propellers to a slightly smaller propeller that was not desired because it didn't fit the shafted motor. Is that correct?
Yeah, that's correct.
So propeller size is very critical to performance. So why didn't you guys just make an adapter or like drill a bigger hole into like the propeller, for example? Why was that not an option?
So that was an option, but when I was in the lab and I asked about it, we realized that the accuracy of the drilling of the hole in the propeller would severely impact the actual propeller when it's in the air. So we didn't want to firstly make that mistake. And secondly, we also realized that when we calculated the propeller diameter to be around 20 to 25% of the wingspan, the propeller that we selected now, 10 inches, is actually much closer to 25% of the wingspan. It's around 10.75 inches. So it's one of those cases where we thought one propeller would be good, but then we actually start making it and we realize that there's another one that's better suited.
Okay, yeah, that's convenient. Sometimes things work out that way. All right. Why is your battery like? I guess it's just more overpowered. Like, how'd you size your battery? Is the question I have next. How'd you size it?
So for the battery, it was one of the ones available in the lab, and it was also I think it's suited because it was a 4-cell battery, and this was compatible with the power consumption. So with the 4 cells being each 3.7 volts, in total making it 14.8 volts, it was enough for us to achieve our power consumption.
How did you
We didn't want
calculate
to
that?
opt.
And those
Sorry.
were based on, we based those on motor spreadsheets from manufacturers. Most of them are in Innovative Designs, I think is the name of the website, which is a power system company that sells like these motors from multiple companies.
So you just look at like current draw of the motor and like voltage of the battery.
Yes,
Check.
to see, yeah, each battery size, like cell size, I guess cell amount or voltage would result in a different power consumption. So we needed
Okay.
4 cells. If we went with 5, that might have been way too much power. If we went with 3, it would be below 339, which is what we needed, I think.
Okay. That might have been some good information to include in this report, just how you select your battery and stuff as well, because this will likely never happen like in like a project to this scale. Like again, like how do you know like all the stuff actually works once you do a math and show it? And I guess that's another question I have for you now is like, how do you know that the motor or the battery wasn't going to overheat or explode?
So to be completely honest, we didn't think about that at first, but later we reflected on that and we realized that maybe since this power system had a flight time of around between like 13 and 15, something like that, minutes, and we would fly for much less than that. Like our maximum time was 5 minutes, but most flights were only 2 minutes to do the 3 laps and land. So like we wouldn't even get close to using the battery for that long. So we thought maybe that wouldn't be a problem. But being completely honest, we didn't consider that at first when selecting the battery.
So do you know what the formula is for heat generated from like electricity?
Not really.
Okay, the formula is I²R. So your heat generated is a function of current draw. And if your motor is operating or pulling basically towards this larger side of the duty cycle with larger current, then you are going to heat up exponentially. And so if you have a motor that's basically always operating like drawing as much current as it can, then that is a risk. John is something he communicated that risk to us last year. That's something that can happen in just like a 5-minute flight. If you draw too much current, then you could smoke a battery or a motor. So just something to keep an eye out for. Again, like these are off-the-shelf components. It's only a 5-minute flight, so it's 90% likely not a risk, but it can happen. So it'd be a good thing for you to consider in the future. Okay. Let's talk about your wing structures. So the yield stress of the proof cement PLA, where did you get that from?
Source 13, if you want to go to the references.
You don't have to check the references, like what that reference is a spec sheet, or is it like a?
Yeah, that was the Prusament PLA spec sheet.
Okay, is that adjusted for anisotropy?
What?
I beg your pardon?
Is that yield stress adjusted for anisotropy?
No, I don't think we adjusted.
Okay, do you know what I mean when I say that?
Anisotropy has to do with like the directionality of a material.
Yes. So whenever you're printing a material, it's not really isotropic. So usually the Prusament PLA, the way they actually get that yield stress is like along the axis of the print. The majority of your load is going to be actually in the layer direction. So your actual yield stress would be probably significantly lower. So your factor of safety of 3 probably accounts for that, but it's probably much lower than you think it is. So whenever you're looking at basically any composite material or even 3D printed material, you should always adjust your yield stress for account for anisotropy.
All right, we didn't realize that. Thank you very much.
Okay. Another thing, what was this loading scenario that you were simulating?
5 Gs basically. That's why we used a maximum loading factor of 5. That would be like experienced during like takeoff or something. It was the most load that we expected our craft to experience.
Do you experience 5 Gs during takeoff?
That was what we researched was a typical value for RC aircraft. And I mean, I've heard 2.5 is like a good one. We used the higher value that we researched just to be safe on the safer side.
So reference like 5 Gs during takeoff is extremely fast. That's like probably like faster than most commercial cars just in terms of acceleration. I think you're actually referring to deceleration here, which would actually be during landing. But the point still stands. You calculate based on 5G, so good job there. Did you also just look at nominal flying in like worst case scenario of like stall characteristics in the sky, or to just landing?
I just knew that that was like a maximum typical value for RC aircrafts. I'm not sure what phase of the flight that's for, if I'm being honest.
Okay, so the 5Gs is most likely during landing because you have a rapid deceleration when you hit the ground, and that is your worst loading scenario. Another thing that you should account for as well is combined loading from lift and drag, both acting on the wing. So that's at your maximum airspeed, at your stall angle, will usually give you the highest lift and drag on your wing. So that's something to check in for as well. You should also account for these shear forces that are going through the wing itself because of are acting in the direction of the layers of the print. So all things to consider. Were you gonna say something?
No, I was just saying thank you.
Okay. I lost my train of thought. Next slide, please. Yeah, so why did you approximate the airfoil to be, oh, sorry, before this question, did you assume a infinitely stiff like fuselage when you did these wing loading calcs?
I did not consider the fuselage in honesty, but I'm assuming that that means yes.
Yeah, so I think that's why you guys fuselage probably failed on the first run. All that load the wing could probably withstand, but all that load is being reacted at your actual point where the wing is mounted. So you have to also do some calcs for your attachment points on the actual fuselage. You can have a super strong wing, but if your plane is, if your fuselage is weak, then you're screwed.
Yeah,
Um,
that's the issue we ran into, so I think you're right.
Yeah, that
Yeah,
was our biggest problem why we switched to a high wing design so that we could make sure that our wings are all one piece and removable so that the fuselage doesn't have nearly as much stress acting on it trying to support the wings.
Yeah, not having those two holes there would decrease stress concentrations, even though we still had one at the top.
okay. Why did you approximate your airfoil to be an I-beam? If I understand correctly, you said in the first iteration, you didn't have a spar running through the wing. Am I correct on that?
Correct, we did not.
Okay,
We
so
had
why?
the connections between wings, which were, since they were done in sections, each section had a wall. So I guess the first time we approximated those walls is like the spar, the TW.
So you had ribs, but you didn't have a spar.
Yes, yes, we had ribs, yeah.
Okay. So if you just have ribs, that's primarily just going to stiffen your skin, but it doesn't introduce a real load path that goes through your entire wing. The issue with approximating your airfoil as an I-beam is that you're assuming that the flanges, or in the case, in this case, is actually stiff enough to transmit load. Let me ask you a theoretical question. If you have like a block of steel nested inside of an aluminum cylinder, and you put up like a block on top, say they're the same length, you put a block on top, which one takes up majority of the load? That might have been like
The steel mostly because it has a higher, it will deflect less in response to the force.
yes. So the steel is significantly stiffer in that case. So it will take up the majority of your load. In which case, like the point I'm trying to like get here is that your actual webbing or the skin of your airfoil is not really stiff at all, especially in comparison to a rib or a spar. So I would say that this I-beam analysis is invalid for that. And generally, if you want to do sort of structural analysis, it should be for sizing your actual spar.
Okay.
Okay. Let's see. I'm sorry, I have a list of questions here. Can you go to the next couple slides? Maybe the stability slide, I think was next. One more slide after this. I think it's a table of all your stability values. Okay, so I think this is just a mistake, but you have your stability criterion as positive for CL beta and CM alpha, but then you have negative values. Is that just fine error?
That was
Yeah, that was a
I'm sorry,
type. Yeah,
that
that
one.
was,
Okay.
yeah, that was a typo, but they are supposed to be the values that they are supposed to be negative for CL beta and CM alpha and positive for CM beta.
Okay. I'm sorry to call it out. That's just nitpicking, but I just wanted to clarify. Okay. Next couple slides. You mentioned somewhere, it's no more to site stability stuff, but you mentioned somewhere that you changed the material of your fuselage from lightweight PLA to regular PLA to strengthen it. Why was that your first choice to strengthen the fuselage?
Well, so the first thing that we tried to do was thicken make it thicker. So at first it was 0.4 millimeters and we changed it to 0.8 for the second test flight. But we noticed that it was maybe a little weak still. So we spoke to another group and they said that they were using PLA, and we researched on it and we figured that it would make the fuselage even stronger, taking into consideration that we also added double the thickness from the first test flight.
Yeah, so the issue with that is that you're increasing the density of your material pretty significantly. Do that, the plane is going to be a lot heavier. I don't think that was really like the proper way to go about it. Like, you could have strengthened your fuselage just by adding ribs on the interior, and that would have maintained lightweight structure, also adding some extra moment of inertia.
Yeah, but as also as I mentioned in this part, this was also done taking into consideration that the motor had enough power to generate the lift that we wanted, even if we added more weight, because we knew that adding PLA would cause it to be more dense and therefore weight more.
Okay. And then again, this is kind of also counterintuitive to what I just said, but another option you could have gone with, I think there's an extra credit requirement for the class, was to just reinforce it with composites. Was there a reason you guys didn't go down that path?
Yeah, the main reason was because, to be honest, we started assembling things pretty late. I mean, that was completely our fault, of course, but yeah, our first test flight was pretty late, so we didn't have as much time to to make the carbon fiber parts.
Okay. What was the reasoning for having the plane come together late? Was it just like a scheduling issue, a complex design?
Yeah, I think it was a scheduling issue. One thing that we should have done to make the process faster was assigning shifts, because sometimes there would be like 10 people in lab and some people wouldn't have nothing to do. And sometimes there would be no one there, so maybe if we had people come in groups of 4 or groups of 3, we would be more useful in our time there.
Okay. If you could go back and change like one thing about the entire process or like the design, what would you guys do?
I'm pretty sure on the last slide we mentioned all the room for improvement that we could have done for the project to gone better.
One thing, like this scheduling thing, was one thing I really think we should have done. And other thing is, we should have worked like we worked in the last few weeks since the beginning. To be honest, like we should have put as much time as we were putting it at the end, because we were there every day and like doing this. So yeah, I think we should have started a little earlier on that.
Yeah, I think that's something that people tend to underestimate in a build style class for senior design, is that the build is probably the most time consuming part of the process. Even if it is being 3D printed, it's a passive process, it does take a ton of time. So I think in the future, if you're starting a project from scratch like this, it's very important to plan out the entire process before you begin. And also just have like shared communication channels like OneNote. I know you guys have access to PDMs as well. It really helps with just managing everything. We set out a calendar very early in the season. Okay. Did you guys do any pre-flight tests?
Is that more like testing the electronics?
We tested the control surfaces, but we didn't do. I guess
we did test the control surfaces. We also like went down the runway to see if we could like stare it on the runway a couple of times as well. Not sure if that's what you're talking about when you said.
So you did taxi testing and you did control surface testing?
Yeah.
Did you do any CG testing?
Sorry, what was that?
Any
CG testing? Yeah, we held up the plane to figure out where our CG was basically.
Oh, CG. Okay, yeah.
Were you guys off like on the first design?
On the first one we were off by a lot. On the second and third one, the CG was, I guess, more around like the half quarter of the wing instead of the quarter, so it was a little bit behind where we wanted it.
Yeah, that's pretty standard. It's really hard to get CG where you actually want it, especially with these type of materials. I applaud you guys for not just smacking like a 10-pound weight in front of the point to try and fix that and actually redesigning it. So good job there. But yeah, just overall, I would like to see some more quantifiable goals and maybe just better trades throughout the entire design process. Otherwise, it's less of a presentation. It's more of like a brochure. So if you can have trades that justify all their choices, that'd be great. It seems like it was kind of hard to follow the presentation in a couple parts because of the power to weight thing, for one example. Thank you for not doing bad FEA. I've seen some other groups do bad FEA. But yeah, that's all I got. Good job, guys. Thank you.
Thank you so
Thank
much
you.
for your
Thank you.
feedback.
Thank you.
Thank you.
Dr. Trump, do you have any comments?
No, I sadly missed most of the presentation because I'm putting out mechanical engineering fires, but I wanted to catch the last little bit of it was because I was available. So, but no questions. Thank you.
Thank you. I think Jacob gave very professional, very detailed feedback on almost everything I could think of. So just some comment in general. Let's say first start from pure presentation wise. I gave about 1 hour lecture on the how to do the presentation, how to prepare the slides. How many of you were there in the class?
I think about 3 of us.
3. Why the rest of you not there? Because I intentionally did it in the class during the class time, so there should be no time conflict.
Yeah, I guess like at least in my case, we hadn't had class in a while, so I had other things scheduled, but like I know it was during class time. We should have been there, of course.
I know that for most of us, I think that was the second test flight that we did also.
Yeah, I was on the same day as the second test flight, so we spent a lot of time on the field already.
Yeah, we were fixing problems that we had. And
No, we didn't have test flight on the day when I gave a lecture about the final presentation.
That
I
was
know, but
the
I think
one where
you-
we miscommunicated about showing up to the field. So yeah, just our team was there, and yeah, you and like John couldn't make it because yeah, there was confusion the night before at lab.
Okay, so if you check, let's use page 7 as an example. Page 7. I mean, what's the point to put so many words here on the presentation slides? Do you really want me to read, or do you really want me to hear your presentation, to listen to your presentation? Your information, you want to convey your information through your talk, or you expect me to read the information from your slides? When you put so busy information on the slides, it's really a distraction from your presentation. This is not a lecture kind of presentation like, okay, I'm doing a lecture here. You're gonna use my slides for preparing your homework, preparing for your exam. Yes, I need to provide the detailed information, but for these slides, is supplementary. You want the purpose of presentation is conveying the information through your talk. If I want to know the details of information through the reading, I can read your report. I don't need to come to your presentation. So you need to know the goal of these slides. And if you make a slide so busy, I feel it's a lot of distraction. I think for those of you who were in my class, I emphasize a lot. Actually, I put it as the first biggest mistake in the presentation, and I hope it does not show this time in the final presentation, but it's still something like I don't know. And another thing is that a lot, as I think Jacob mentioned this part, is so it's like a trade study. I really want to, because we are doing a design that should be specific to satisfy our requirement. So I want to do this design scientific way. Use some trade study. Let's say, for example, that's from the very beginning on the third page when you start initial estimation, and you use the reference, and that reference is just one aircraft. I did mention that, yes, for the initial estimation, we didn't have anything yet. We do our initial estimation based on the history data. And this history data means it at least need to have several data, but your initial estimation is based on one aircraft.
I think it was based on more. I just
But
think
your
these
reference
slides-
only, your reference, I check reference one, you can check that one. It's only for one single aircraft model.
Okay, then we didn't add it here because I think in the first report, we did include more than one. I think Sabrina probably knows.
Yeah.
There are 4 more aircraft. Yeah, the problem with some of those, they didn't have all like the specific specifications with like the wing loading and stuff like that. So yeah, just going off of that research alone, we didn't know how to ballpark that. And yeah, there's very few that we found on like the market and the resources we looked at. We definitely could have done more in-depth research with like the trade studies to find that information, but yeah, initially we did struggle with finding that.
Yeah, so at least when you do this presentation, make sure that it just cannot be persuasive when your conclusion, your initial estimation is from one single data point. And also it's like, Jacob already commented on this, but I just want to emphasize again, so you want to make the same mistake in the fund report. The page 4, when you chose this NACA 2412, and I was really surprised when I heard you said because of popularity. I mean, we're not in the fashion world. You cannot choose something because of popularity.
Professor, I believe that was maybe like a wrong choice of words. We just meant that through research, we noted that that was one of the most popular airfoils that was used, and we identified the advantages and disadvantages of that specific airfoil, and that's why we decided.
I guess that was a way to narrow down, I guess, the first, like which ones we were going to analyze the parameters on. Even though maybe we should have.
What I heard was like in the end you have 2 candidates, and out of 2 candidates, I heard what you guys are talking about is like because of one is more popular than the other one, so you chose.
No, I think it was more that those 2 were the most popular ones, and then we analyzed the parameters of those 2 and selected among those 2. But I do agree that maybe we should have put more options in that last pool of airfoils, so then we could analyze the parameters on more than 2, like maybe 4 or 5.
Yeah. So even for 2, let's say, as engineering students, the key thing you want to show is your analysis capability. So let's say it's not just what is your final decision. I want to know why you make this decision and why it's a best option. So I would consider, let's say, just use this airfoil selection as example. You give me a table, give me a trade study. These are the candidates, and let's the lift coefficient, moment coefficient, lift drag ratio, like persuading me in a scientific way. You know what I mean? To prove that your option is optimized for your design, for your expectation, for your requirement. So of course, I just use this one as an example. So make sure that in your report, you really include a lot of trade study and explanation why each decision is made. And for the, I think a good thing about this one is the structure analysis. I think the structure analysis did really well. And on page 15, maybe it's some typo or some mistake, or my misunderstanding. Why the stability is determined based on the derivative of then with respect to deflection angles? What do you mean by deflection? Deflection of what, flaps?
I meant the deflection of the craft, or maybe I should have just said relative to the wind. I just meant like the angle of attack and the side
Yeah,
slip
it should be
angle.
angle beta and alpha, but when you say deflection angle, I can naturally connect it to like deflection
To
of,
a material property, I'm
yeah.
sorry.
So it's a little confusing here. So make sure that when you do the write the final report, to make sure the wording is more accurate.
Yes.
And also I personally believe there's nothing wrong with like we always have like several iterations for the test flight, and I do agree that each test flight you guys are doing much better than the previous one. But personally, I do not think the first test flight has successful takeoff. because a successful takeoff means that your airplane needs to reach a certain height.
I wasn't aware of the actual
That's a fair
criteria
point.
for it. We got off the ground. We were kind
I
of
think
happy.
like we were also debating whether or not to say that. So yeah, it's
I
very
personally
50-50.
do not think that is a successful takeoff, because it's more like it's just leave the ground. But the definition of takeoff means you leave the ground and climbing to a certain height. And if you reach that height, and then you crash, yes, it's successful takeoff. But your aircraft is like it crashed right after takeoff. This yeah.
We'll change it till we got off the ground.
Yeah. So but there's nothing wrong, because I do believe like second test flight is much better than the first one. So there's great improvement, and I really appreciate that. So there's nothing wrong with that. Just when people, well, I think for a lot of people, when they watch the first test flight video and see like successful takeoff, then probably there's some confusion there. And you mentioned the carbon fiber spar for the second test flight. I don't remember that. So did you really use a carbon fiber spar in the second test flight?
Yeah, we used the same spar that you had showed me in class.
Oh, okay.
Yeah.
Because I feel like the wing at that time was like really flexible, so I don't really know if you really use that one.
No, we had them.
Okay, that's good. So overall great job, and I feel like I'm glad to see that even though there's no successful landing or anything, but the last one, it showed that it's able to take off and it's able to fly for a certain amount of time. Maybe well, the weather is one reason, and also I need to admit that I'm not complaining about the pilot or anything. I want to admit that the pilot training this semester is not enough. It's really hard to have a mature pilot to be capable handle of different flight situation and windy situation within one semester. Because if you see John or Mark, they have many years of experience. So they probably do that every weekend. So the pilot training is not enough. That is one cause of the crash of flight, but it's not a pilot fault, I want to say. So don't blame the pilot. I think every pilot in our class did a great job.
That's one thing I wanted to mention as well. I think you guys said like it is really hard to fly these things. First of all, like the plane weighs like 2 pounds, but one thing that I heard you guys mention a bunch for a sighting for a failure to land properly or to take off properly was poor planning on like weather days or like wind that's too windy. I don't think it's fair to really blame the weather for like the plane not working. I think it should be design criteria.
Well, we weren't really blaming the weather for not working. The weather, like on the second test flight, we had like a really big gust of wind that like kind of pushed the plane back towards the tree line. And then I kind of like just lost sight of the orientation of the plane, like which wing was left and which wing was up, which wing was down. And I think because I lost orientation, I rose too much to one side, and that's what caused us to crash into the tree.
You know, also, if we would have waited one more day, the winds would have died down much more. So maybe if we were just more patient overall, but this was our new high wing design. So I think we were just
We were eager to get it up.
antsy to get out there and try the new design, when in reality, like 24 more hours of waiting wouldn't have killed us.
Yeah, I feel like the wind might be the reason why it crashed, but it's not an excuse to why it crashed. Like, of course, we should have predicted that and designed for it.
Yeah, so when I want to say that when Group 1 had successful flight that day, the wind was 20 miles per hour. I was there. So
Yeah.
so